Okay, I am recording now. Okay, welcome everyone to the first event of ACMEI in the fall quarter. This is our introduction to AI and neural networks. This is going to form our first series in this quarter, which is the neural network series, where we take you from scratch, from using NumPy to programming neural networks to using different tools to make neural networks and optimize and train them. And usually we culminate with some kind of competition at the end, so you can apply what you've learned on a custom data set we make. But this first workshop is basically just going to cover the basics of AI and with a focus on neural networks. So Edward, take it away.
Okay, so that's the check-in code. Currently, it's beep boop, and you can use it to get, or right now, it hasn't been implemented yet, but later on, there's going to be an ACM store, and you can use that to buy cool merch, like stickers. Yeah. So what is AI? AI is a field devoted to exploring methods to exhibit intelligence in machines and produce intelligent agents. It can be as simple as like an if statement. You've seen that meme where it's like, if this, do that, and then you can consider that AI. And it can be as complex as like a 100-page research paper detailing how you can model the complete brain using just a really massive neural network kind of things. So yeah, AI has a really large spread. And if you look at the second picture, those are some of the subfields in machine learning and AI, such as NLP, robotics, autonomous vehicles, and vision. So just some numbers about AI. 37% of organizations use AI. There's around 4 billion devices already powered on using AI-powered voice assistants, such as like Siri, which has a lot of AI in it, surprisingly. And there's also 97% of mobile users are already using. Yeah. And also, in 2017, Netflix saved almost $1 billion by using machine learning to optimize their processes. They mainly use machine learning just for their recommender systems by essentially optimizing the sort of movies and also TV shows that each user gets, as opposed to just like manually scraping data sets for what they're interested in. Some other history, that's a picture of Alan Turing. And also, if you look at what Google has been doing, Google, Facebook, TensorFlow, DeepMind, Amazon, OpenAI, and 3 of which are owned by Google. So there's basically just a lot of stuff that Google has been doing. So do you want to speak more on this slide?
Yeah, so concept of AI has actually been around for ages, but hasn't blown up until like 2012, which was basically when deep learning became very popular, which is something we're going to talk about through these lectures. Before it was only science fiction, but now is not science fiction anymore. It gets even to the point where a really popular test known as a Turing test, which just basically tests whether or not you can determine is this person texting to you a bot or a human. Right now, we can create AI that can solve that test. You literally cannot tell the difference at sometimes. Supposedly, the first attempt of AI was called a logic theorist. There's a link. I'll send a link of this into the chat. This was by Alan Newell and a few other people trying to mimic the problem of solving skills of humans. Didn't work great, but it was like a start. It was like an example of something that tried to do AI. And one of the more popular early successes came from what's called ELIZA, an early NLP, natural language processing computer program, which just basically means they take text, process it, try to understand it, and make an appropriate reply. This was created from 1964 to 1966 by Joseph Weizenbaum. Chatbots are AI, by the way. It demonstrated the possibility of AI, helped kickstart enthusiasm into AI and NLP, and truly demonstrate something out of the world and its ability to kind of just simply respond and interact with humans effectively. Moving forward, a lot of fundamental work from lots of different researchers, from David Ruenhart, Javis McKellen, who was at UCSD at one point, on lots of different texts, such as parallel distributed processing, deep learning, neural networks, convolutional neural networks, all these like shebangs, led to where we are now with mobile powered devices full of AI in it, like Instagram filters, Snapchat filters, recommendation systems on Netflix, Siri, all that stuff.
So this is just like a tree of some of the most common terms that you hear in this field, and I'll just briefly explain a few of them. One of them, like the biggest one, is just machine learning. machine learning is kind of like a subfield of artificial intelligence, specifically using like computers. Yeah, it's basically like using any sort of like computer to process and also essentially just have the computer learn to do better on a certain task after certain iterations kind of thing. Another big word is computer vision, which is essentially using computers to basically just using computers to learn about images, stuff like computer graphics, like optimizing and making pictures prettier, or just generating like brand new pictures, like using like the face scan kind of thing. Or it can just be things like depth perception, stereo vision, which is using just like two images or set of images and predicting the depth of a lot of different objects. And it can even be stuff like 3D reconstruction, where you give a certain number of images, and the whole point is to be able to essentially map out a room or to recreate like a 3D object. And another cool term is RL, reinforcement learning. This is more along the lines of like robotics, where you essentially don't have the whole purpose is for the agent to kind of explore the environment, and using that exploration be able to draw out meaningful information about it. So it's a lot more, it's unsupervised essentially. And if you just want to take a second to look at it, there's a lot more other words. Yeah. But fundamentally, AI is all about stats, simple or complex. Foundationally, I think generally a lot of people associate AI directly with like deep learning, but there's actually a lot of non-deep learning approaches, such as SVMs, linear polynomial logistic regression, Monte Carlo tree searches, and even genetic algorithms. And none of these use neural networks in their processing, or rather they could be, but they're generally not associated with neural networks. They're honestly just like a lot of like math stuff you can use to do it. And AI is also about systems, computation, and also a lot more math. Where this comes from is to make your system really robust towards attacks. There's a whole field of AI dedicated to adversarial attacks, which is essentially generating images or generating other examples that are very close to the actual one, but the human eye can essentially differentiate it. But to the model itself or to the algorithm, they're going to be like, oh, shoot, it's a completely different one kind of thing. And other computing examples is GPUs, TPUs, hardware acceleration, parallel computing. So deep learning and a lot of these require a lot of computation power. The data sets are really massive. So you need to use parallel computing and just a lot of like hardware acceleration to not just have to wait like a couple years for your model to finally like generate meaningful output. And some applications of AI. I think the most common one that a lot of people know about is automated driving, such as what Waymo is doing with the self-driving car, and also Tesla, which is also doing self-driving car stuff, image recognition, sentiment analysis, object character recognition, and also Westworld-like robotics. Although we haven't achieved that yet, we are ever getting closer to the days when that can occur. There's also email spam detection and a lot of other stuff. Yeah, optical character recognition.
Oh, that's a typo. That should be optical.
Yeah. And a lot of recommendation systems like your YouTube or Twitter feed are usually based on there's a lot of based on like your past experiences in which you interacted with, just so they can select like the best feeds for you. Yeah. So AI is involved in a lot of stuff today.
Yep. So I'm gonna start just talking about like kind of basics of neural nets. So the whole set of our series is basically focusing on neural nets and deep learning. There are a lot of other things like AI, but we can't talk about everything. But basically the first thing is like, what is a neural network? This is something that everyone wants to know. It is quite literally a computational representation of the human brain. And effectively, formally, it is a graph of interconnected neurons that allow you to send in an input and then has some output. So if you think of a graph, if any of you guys have learned anything graph theory or taken a discrete math course, a graph is composed of nodes, like little circles, and each node is connected to another node with edges, these black lines. These black lines represent where data transfers. So we see the two arrows showing where the two input points go through two green circles. That data is transformed, manipulated, feeds into the blue circles. Those blue circles then transform, manipulate that input data into the yellow circle, and that yellow circle then finally produces an output. So for example, this input data could be like, say, housing prices and housing locations. It goes to the neural network and out comes a housing price, something like that. Yeah, and neural networks are almost used in every field in AI. Super important for like forecasting models these days. Something very recent is that DeepMind has been using neural nets to do what's called nowcasting, where they predict the current weather state very accurately to some extent. Or sorry, they predict the future weather state very accurately. We've seen this used, and yeah, Khrushchev was asking about social media websites, and yeah, they also use neural nets of some kind to get you good recommendations. We see neural nets especially used often in computer vision and natural language processing because they're very effective at that. So for computer vision, for example, you have like classification tasks, natural language, you can be generating text, you can be analyzing text, saying, is this text sarcastic? Is this text emotional? Is this text super angry sounding or something like that? So yeah, also great and important is really good to understand some of the cognitive or biology kind of basis for some of these things. So a neural network is based off of a neuron, if you haven't figured that out already. Basically, neurons are things in our brains that do computation in our brain. So the way that our brain works is that we use neurons to make decisions. If you take any kind of decision-making course, or if you take COG 17 or COGS 180, you will basically learn how exactly these neurons are used to make a decision. At the very basic point, a neuron, or what's also known as a perceptron, is a basic building block of a neural network or your brain. And it uses what's called an electrical threshold to determine whether a neuron fires or not. So you can think of a neuron in a macro scale kind of idea is that whether or not your brain says yes or no to some question. It says yes when we reach past some threshold. It says no, we don't. So what is this threshold? It's actually electrical. So everything in our brain is chemical electrical reactions. The key difference between our brains and the neurons, the key difference is that the neurons in our brain fire always at the same amplitude. So when they do a fire, they get over some threshold, they fire a signal to the next neuron along a chain. And this kind of chain of neurons make a decision. But the difference is that neurons in our brain compared to actual neurons that are built with PyTorch, TensorFlow, or whatever you see in computer science, they fire at same amplitude but different frequencies. Whereas neurons in a neural network fire at different amplitudes at the same frequency. The slideshow is online. Can someone send the link? But yeah, so this is just kind of like the biological perspective. If you want to know a bit more, a neuron is composed of these things on the left side. Signals go through dendrites, go through the myelin sheath, out to the axon terminal, and that's where you fire to the next set of neurons. And yeah, and if you want to be even more interested, just some recent research into something called spiky neural networks, which are a closer mimic of the actual brain. Unfortunately, they don't work well, right? They don't work well yet, but a lot of research is going to that. If you guys have any other questions, keep posting them into Zoom or say, just post into the Zoom chat and we will try to get to them. All right, next slide. All right, continued. What is a neuron? So here is a mathematical definition and how you basically program a neuron. So how it works is it has an input and output. It takes a set of inputs, so x1, x2 to xn, which forms a vector, x1 to xn. So there's a tiny bit of linear algebra here, but it should be mostly understandable. Just think of it just like n values. You have x1 to xn. Oh, sorry, my Discord is screaming. Give me a second. Yeah, that's me. I think it was me. So you take a set of inputs, x1 to xn, and then you evaluate what's called the weighted sum. So what the weighted sum is basically for each input, you multiply it by some value, w. So basically x1 times w1 plus x2 times w2 plus xn all the way times wn. This gives you a weighted sum. All this then plus a bias term b gives you the neuron function. or the first part of it, the weighted sum. So the result is then fed through, so after you get this weighted sum plus bias term, you then feed this through a function f, which can be any function you choose. And then whatever the output of that function f is what's outputted from a neuron. So we start with inputs xi, we get an output y. And these are all vectors, basically. So if you think of a single neuron, and we look at this weighted sum function, suppose like the function f is like a linear function, so f of z equals z, like that kind of function. This particular weighted sum kind of formulation is effectively finding a hyperplane, if you can think about it like that way, that splits the set of data into two distinct sets. So if on the bottom, if you're looking at 2 dimensions and you're looking at x1, x2, if you look at the weighted sum, that's basically just w1 x1 plus w2 x2 plus b. That's the equation for a linear line. So if you know what y equals mx plus b, that's basically the same thing. And yeah, and for a formal kind of just word terminology, the function f is called the activation function, and this can be linear or nonlinear. When it is linear, you basically create linear lines and hyperplanes, as we see in the bottom photo. But when it's nonlinear, we have some other quirky things that happen. So another important term to understand with neural networks and deep learning is the concept of weights and biases, and the idea of parameters and what's being trained. So weights and biases, the w values, w1 to wn, and the biases b, these are what form what's called the parameters of a neural network. So a neural network is what's so-called parameterized by these values. When we say parameterized, it means that its behavior is affected by this choice of w and the choice of b. And these parameters are what's trainable. So they're variable and subject to change as the network learns. And as the network learns, these values are changed such that we can get our desired output given certain inputs. So basically to define the overall behavior, and if you want to intuition about what these do, weights for one transform input. A bigger weight wi indicates that a particular input xi is more important as it influences the weighted input z more, usually. Understanding how neural networks work is still basically a long kind of research topic that's still being investigated, but this is one intuition you can use. The second thing is called the bias term. So this is the bias to a neuron, which is something that's always added to your output, regardless of your input. A bigger bias B is basically just indicates that the neuron, so not the input, is more important to the overall network as it contributes to a larger activation, regardless of what input you have. Yeah. Give this to Edward.
Yeah, so the last key component in a neuron is the activation function. And the activation function defines how it transforms its weighted input into an output. So 3 examples of them are ReLU, which essentially just takes the max of the input value, and 0. So as you can see in the graph to the right, everything below negative, anything negative is going to be 0, and anything above is going to be identity. And there's sigmoid and also tan, and those are like the associated functions. And each of these are specifically used for different tasks. Specifically, or rather, they're better or more optimal for specific tasks, such as sigmoid, which is generally used in a lot of classification tasks. Especially, I think the most common thing is called binary cross entropy loss. Yeah, because it essentially creates a distribution or a probability of how likely a certain item is associated with a certain class. And using such a sigmoid function, which has like a curve and an average of around 0.5, which is essentially basically either the class or not the class, it's really beneficial for sigmoid and also for a lot of the initial backpropagation results. And so if you look at the slide in the previous one, there's a difference between some linear and also nonlinear activation functions. So for context, ReLU is a linear activation function, whereas sigmoid and also tan are nonlinear activation functions. And so the purpose of, or rather, yeah, and the other one is just identity throughout. And so the purpose of these kind of nonlinear activation functions is that we want to be able to model much more complex data. Essentially, with only linear activations, we're extremely limited in the number of predictions that can be made. Think kind of like linear regression. And however, tasks like image classification are super complex. The data is in a very high dimensional space. So it's very difficult to just use like linear linear lines to just kind of like isolate the different classes of said images. And like if you look at that picture, yeah, like that's gonna take a lot of compute and a lot of neurons and a lot of layers just to figure out what that example is. However, if we use like a nonlinear activation such as tan or sigmoid, we will be able to measure or model the curves much more easily, and as a result, converge and also just have a much more efficient network. And the other thing is that if you consider it from a more learning perspective, linear activations have a constant learning, which means that the backpropagation of a linear function is just a constant. Think like when you take the derivative of y equals mx in terms of x, the derivative essentially is just m. And that's not that good because it doesn't offer any relation between the input and the derivative output. And the other thing is that you can't have multiple layers. Recall that in like matrix operations, if you take a lot of matrices that are all, and you just take the linear combination of all these matrices, it's not, the internal ones don't actually do anything. It's only the outer two that actually model anything. So if you have a lot of linear layers together, it's essentially just one giant linear layer, which isn't really effective either. And as a result, that's why we tend to use a lot of nonlinear activations, which allow for backpropagation because derivatives are non-constant. Like if you try to take the derivative of like sigmoid, that's definitely not nonlinear activation. But is it true? You're not sure. And also you can have multiple layers that can be represented and also have all of them have full effect.
Yep. So next couple slides, we're gonna start doing something like code and basically how do you implement a neuron in Python. So we're using Python as our main coding language, and we're also using something called Jupyter Notebooks. So if you want to follow along, we have all the code upline. So let me go find it real quick. We have this GitHub repo. Please start it. This is super useful. This is where we put all our workshop code. Yep. So Joseph already sent it to the chat. But basically you can follow along here. So you see us, we wrote functions in Python using NumPy. If you don't know what NumPy is, you have to know what Python is. If you don't know what Python is, sorry. But if you know what if you don't know what NumPy is basically stands for number Python. It's basically a very common and highly useful scientific computing tool. So they can calculate like different kinds of functions, handle matrices, handle matrix multiplication, whatever. But let's go through a couple of simple examples of how do neurons make predictions. So here's a super example. This is a 2-neuron network, basically 2 layers. So since neural networks are a representation of a complex mathematical equations, we can basically just model anything. So let's look at the equation y equals 3x plus 5. And let's look at a model below. So our model here is we have one hidden neuron in the middle. That's our output neuron, sorry. And you have one input neuron that takes in the input x1. So if x equals 1, we multiply it by 3, we get 3. And then we plus the bias 5, and that gets an output of 8. So you can see how this neuron on the bottom gives you a complete replica of what this function is. Anyone have questions about this? And you can also see this code here. So for example, here, this is where we start defining the code. This is an example of using the 2 weights we've defined, or sorry, the bias we've defined to make a linear function. So this is as simple as what you do in high school math, mx plus b, basically. Slide. I'm gonna go with something a bit more complicated. So we're gonna do what's called an OR gate. If you've never heard of an OR gate, this is from discrete mathematics, or physicists might know about this from electrical engineering, or anyone who studies digital logic. This is quite common. So an OR gate basically takes 2 inputs, A and B. If A and B are both 0, we output a 0. If A or B is a 1, we output a 1. So 1 you can treat as a true, and 0 you can treat as like a false value. So the perceptron rule is that if we want to model this OR gate, what do we need to do? We need to be given 2 inputs. So we define 2 nodes as x1, x2 are 2 inputs. And we define 1 output node that outputs a value. And what we're going to define is that if this value outputted by the final node is above 0, we say it means true, an output of 1. If it's below 0, we say it means false, an output of 0. So if you look at this example here, you can try to make yourself understand that indeed this neural network setup replicates the outputs of the OR gate. So for example, if we plug in A equals 0, B equals 0, they're both multiplied by 2 plus a -1, that gives us a total value of -1. And that means we predict false. So that's correct. If any x1 or x2 is equal to 1, then the weighted sum is at least greater than or equal to 2, you subtract 1, you're always going to have a value greater than 0. So this output will always be 1. So you can kind of confirm to yourself that this is a correct implementation of the OR gate using neural networks. Any questions about this? All right, great. Let's take an example. So this is like something you guys can work on yourself. Here's the problem. It's a little bit harder. We're going to try to write a function that takes the average of 3 numbers. Obviously, the answer is already in the Jupyter notebook, but if you want to type in the chat, let's see how you would do it. Let me give you guys like maybe a minute to try to write down a solution. But example is like given 3 numbers, A, B, and C, take the sum and divide it by 3, basically. We want to get the average of the 3 numbers. So the question here is, what are your 3 weights and what is your 1 bias value? What values work? Anyone want to put into the chat what the 3 weights might be? Turn the light on. Yes. Well, if you look ahead in the slides, you see the answer. If you're just following lectures, you won't see the answer. But yes, that's correct. The answer is all the weights are 1/3 or 0.333. Reason why is we're taking the average of 3 numbers. If you think of an average function, the average function is actually a weighted sum. So that's actually exactly what a neural network does. And all we do is just set the bias term to 0 and set our activation function to be like an identity function, where it just reduces the value. So that works perfectly fine. Here's a slightly harder one. We're going to take this example and show it. So here's the absolute difference function. So what happens here is that if we take weight 1 to be 1, weight 2 to be -1, b equals 0, and a linear activation function, or identity, we can actually replicate the, the activation function here is a parametric ReLU. So basically, if x is greater than 0, y equals ax. In this case, y equals -x. Sorry, I read this wrong. So the activation function here is parametric ReLU. So what we're doing is that if x is greater than 0, the input, we return x. If x is less than 0 or equal to 0, we return ax, which is -x. So this is a very simple way of making an absolute difference function. We basically just define the absolute value function as the activation function, and the weights we set it up so that we can compute a difference value. Yeah, so someone is asking, can a parametric ReLU be learned? Yes, it depends on what you're doing. So if you have a bunch of data that corresponds to a parametric ReLU function, you can learn a model that mimics a parametric ReLU to some extent. It will depend a little bit on what identity function you use, but let's say that you don't have the parametric ReLU function and you're using like say a ReLU function, not a parametric ReLU. The neural network will learn the appropriate weights to mimic a parametric ReLU as close as possible. It probably won't get it perfectly correct, but it'll get very close to it. All right. Here's a really hard problem. I don't know if any, this will take a little bit more time, but this is trying to show the example of what happens when you have multiple layers and how you can do more things. So with multiple layers, you can model more complex equations much easier than one giant layer. So here's an example. We want to model the function 1 less than absolute value difference of x1 minus x2 less than 3. So if it's true, output greater than 0. Otherwise, output less than something less, output a value less than 0. So you can imagine that part of this function has already been done, right? We've already done the first part, which is the absolute difference function. So could we use a previous neural network, add something to it to make it such that we can then make a decision function out of it instead of just getting the absolute difference? Yes, multiple layers is pretty deep. This is called deep learning already. Well, except the learning. We haven't done learning yet. We're just hard coding weights. We're going to do learning next time. Anyway, anyone have any thoughts about how to build a model for this neural net? What would you add at the final layer? Suppose that you already have this previous absolute difference function, absolute difference neural network. How would you extend that network to then give a decision? If function, I guess you could. You could write an activation function that says if this value is between 3 and 1, output one thing if it's not output another thing. That's actually possible. And actually, if you do some research into what's called auto differentiation, you can differentiate an if function. But anyway, here's one way of doing it. This is more of a quote unquote elegant solution where it's just using what we have already. You can actually just add 2 more nodes. So you add a parametric ReLU function and then you add a tanh function. And this will actually exactly produce what you need to do. So Vincent's close, you can use a sigmoid to output a probability of it being in that range or not in that range, or you can use tanh. Tanh and sigmoid are actually the same functions, really. It's just you can rescale it effectively to get the same function. Or a similar function, sorry. But yeah, this is a little bit more complicated, but if you follow along the code, you can see how this works and you can try it out yourself. Any questions about this? There's gonna be a little bit more math next lecture or next workshop. But we're gonna take you guys through it about how to like learn these weights and biases instead of hard coding it. Yeah, the last one's a little bit more difficult, but what you can understand is the first 2 layers, the X1, X2 input layer, and then the first parametric ReLU, that's just a copy of our previous model here. So we already know that the second layer, the first parametric ReLU's output is going to be the absolute difference value, X1 minus X2. So now given the absolute value of X1 minus X2, how do we decide if it's between 1 and 3, just using some simple math and not an if statement? Well, what we can do is we can give it a weight of 1. So we just put through that value into the next function and we run parametric ReLU again. So let's look at an example. If the absolute difference is, let's say 1, right? Or sorry, let's say it's 2. Because 2 is greater than 0, 2, and then we put the bias term -2, that gives us 0. Because 0 is actually just 0. Parametric ReLU produces a 0. 0 goes to the next node. 0 times -1 is still 0. 0 plus 1 is 1. Tanh of 1 is greater than 0. And that gives us a true value. So our original input was an absolute difference value of 2. That ended up producing a value of 1 after a tanh function. Now it works. To try to understand a bit better, what's basically happening is that the second parametric ReLU is telling us yes or no. It's giving us a value that tells us whether or not the function x1 minus x2 is between 1 and 3. Once we know that, we use a tanh to scale the value such that if it's less than 0, we produce false. If it's greater than 0, we produce true or something of that like. Highly recommend writing the function out yourself and you can kind of see how it works. All right, next thing. Oh, Edward, am I doing this slide? I think I'm doing this one, right? Or
Yeah.
are you doing this one?
Yeah, you can do it. It's
Okay.
finished.
So something really important that we're going to start covering even more, and it's a bit more linear algebra, unfortunately, but this is something that powers a lot of deep learning, is the concept of vectorization. So one thing is we can't just hard code everything. And another thing is that matrices bring much higher performance. And this is quite important in all of machine learning and a lot of AI. So for an input layer of n neurons, we can actually vectorize it in terms of the weights. So we will fit an input vector of x with n values. An input vector here being x equals x1, x2 to xn. We can fit that into a data structure called a matrix. And this matrix is basically just a list of items. Yeah, this is linear algebra. Welcome to linear algebra. This is probably as much as you need. So this vector x will be our input. And then we also have our concept of weights and biases. So we can generalize these weights and biases to the concept of matrices and vectors. So we can have a bias vector, which is b1 to bm. And we can have a weight vector as well, which is an n by m by n matrix. So this example is showing what will happen when you take taking inputs from a previous layer of n units going to m units. So a little bit complicated, but if the next layer, for example, of a 2-layer network has m units, m output units, that means we have m biases. So that's why the bias vector is of shape m. There's m elements. The weights vector, remember that we're multiplying this first by the input vector. Some quick math, when you multiply this particular weight matrix as m by n by a 1 by n vector, a column vector, you get a 1 by m matrix, which is also m by 1 by n column vector. And then you can add them together and you get the output vector y. Highly recommend looking up how to do matrix multiplication and addition. That's all you need to know to do matrix multiplications in your networks. And yeah, we have this code on our Jupyter notebook as well, this vectorization. We show how to do this with NumPy, so it's quite easy. And we highly recommend doing matrix multiplication with NumPy because your own implementation will probably be very slow. There's a lot of optimizations that come together when you write high level, a super low level C code to try to optimize matrix multiplications. And this powers basically everything. Without matrix multiplications, we cannot do anything basically. But we can now show an example of, we can now show like a vectorized example. So for example, back to our average of 3 numbers is quite simple. A vector example would be basically one weight matrix composed of W1, W2, W3 in a 1/3 matrix matrix. The reason why it's 1/3 is because we have one output value, but 3 inputs. So then our input vector X is composed of X1, X2, X3. And when we do our function to prove the average, we simply just do W times X, and that gives us the average. Any questions about this? Can we get an SVM implementation in NumPy? I mean, you have to code the optimization for that, but there's actually a direct solution. So not that hard. All right. Here, oh, the activation function for the average of 3 numbers is just identity. So nothing funny for this one. So you pass in the weights, these weights, and then you take the identity function here. And you suddenly get the average 3 numbers using neural networks. All right. So I'm going to show you guys a really cool tool for you guys to play around more with just more complicated neural networks. This is where we got one of the pictures. But this website is super awesome. It's called playground.tensorflow.org. This uses what's called TensorFlow, specifically the JavaScript version of it. Yeah, I think Garrison Carroll uses this a lot. But basically, you can show different kinds of data. So, for example, let's say we have a simple separatable data. The problem here is a classification problem. So you can design your own neural network, add as many layers as you want, add more neurons. Let's say add a ton of them. And then you can press play and it'll start training. It'll try to fit the model such that I can classify everything correctly. So you'll see that for certain models, it can do it well. For some other things, it can't. For example, when you have 10H activation with this kind of setup, you can't really model this particular function. Not very well. If you do ReLU, maybe, let's see. Nope, ReLU also doesn't work very well. But yeah, anyway, lots of different things you can try to do. You can also try, I don't know. And also a really cool thing is that this shows you the weights at each neuron. So it kind of tells you what each neuron is doing. So you can kind of see that each neuron here is like a linear predictor. It tells you it's going to classify one side here and one side there. As you add more layers, suddenly the function becomes different shapes and becomes more advanced. Shader graphs, yeah, kind of. I did try using different activations, but I actually don't even know if you can model this one. This is like, you need a lot of layers or something. I don't know, add a shit ton. Nope. Anyway, you try other things, see what happens. This is actually not going to work very well.
So you're supposed to use different features. You cannot use the linear x1, x2.
Oh shit. Okay, yes, sorry. I gotta use different features to sell this one. Yeah, there we go. That one sells perfectly. Someone's asking, is college or CSE classes are good for people doing ML with bioinformatics? I unfortunately don't know, but if you ask in our Discord, someone will probably tell you an answer about that. There's a couple of people who do bioinformatics in our Discord, so you can probably ask them. Anyway, have fun with that. Here's our resources. We have the playground, and then we have our code. We'll stick around for a couple more minutes for questions, and that'll be it for our event today. Thanks for coming, y'all.
Oh yeah, quick plug. So ACM General has a ACM projects, and if you guys are interested, ACM AI will also be running projects this quarter.
Yep.
And the due date, the deadline for the applications is tonight, and we accept people of all skill levels. So yeah, it'd be pretty cool if you guys applied to it also.
Yes. Let me try to find information about this. Our projects page is somewhere.
Wait, where's the link to this?
Here's the application form. I think heads up, I'm just going to say this ahead of time. We're not going to be able to accept everyone who does AI, who wants to do AI, because we have way too many applications, unfortunately. And we only have so many people to help mentor. And we do want to maintain a certain amount of quality. So we can't mentor everyone, unfortunately, but we're going to try to get to everyone. And yeah, so there are project apps each quarter. As long as you're persistent, you'll eventually get accepted into the project application. So usually we'll defer you to next quarter or something and hopefully you get in. So we have some people who've been deferred 1 quarter or 2 quarters. We try our best to get people in based on how early you applied and based on your interest. Application link, yes, I will copy the link here. I think it's acmuro.com/projects app. Copy message. Oh yeah, and other things that we're considering doing this quarter that we're not sure if we're gonna do is we're considering having a reading group again. So if anyone's interested in like, let's say finding a paper, reading it and like discussing it with everyone. So we're gonna have an open discussion about the paper, what's good about it, what's not good about it. Talk about different topics in AI. This is for maybe slightly more advanced people. We can do that. If you're interested, please do this. If you're interested, please go to our README channel and click this button here. This will give you the AI reading group role, and this means that you'll get all announcements related to AI reading group. What's going to happen is that probably at the end of this week or next week, we're going to put out a poll to see how many people are interested in coming, and then you have to sign up. So we want people to sign up just to make sure, or you have to do some kind of sign up. That way we know how many people are coming, because usually we won't host it if there's not enough people. And what will happen is that each quarter or each couple of weeks, we'll pick a paper, have people vote on it, and then we'll talk about it. So if you're slightly newer to AI, you can come and listen. If you're more advanced, you can come and discuss, bring your own points, bring new papers you think are important. Yeah, any other questions? Oh, if you haven't done this already, so our website is down right now. We're currently fixing this. Like you can't log in or register. Usually if you can log in and register, that signs you up to our mailing letter and also gives you access to our competitions, usually. We had a couple other previous competitions, like we had a hide and seek competition at one point that ran a couple, I think 2 years ago or a year ago. This is an example of what happens. You have these numbers chasing each other. You can also see an interview with the winner. We also have other things that are going on. Other events, you can see our events on our website as well. Our next workshop is the intro to learning. When will the website be back? I have no idea. We're working on it right now. Something's wrong with the server. But for now, please just like use this sheet here. We're gonna add everyone later to our mailing list. But basically, you can just add this. We're just trying to get a sense of who are the new people here that couldn't access our website, basically. Wow, that's a lot of people. Yeah, so please add your information here. We're just using this as a temporary thing just to add new people to our list. So, yeah. Ooh. A lot of these. Victoria Vincent. Oh, wait, has it been broken for 2 years? I didn't know that. I thought it only been broken over the summer.
Wait, can I even log in? Wait,
No, you
what is
can
the
log in.
password?
I think something happened to one of our databases that went down. It was working at one point and then it stopped working.
Wait, I don't remember my password. Do you remember my password?
I don't remember your password. I'm not giving you one.
Damn it.
All right. Bye, Zichen.
See ya.
Yep. Also, if you want to apply to ACM AI projects, you have to choose AI as your first choice. Otherwise, you will not get it and you will not be considered. Yep, no problem.
Oh yeah. Also, if anyone's interested in like mentoring a group for AI, that'd also be pretty cool.
If you think you have enough AI experience, we're happy to interview you and then see if you can be an AI mentor, because we are very understaffed.
Yeah, so essentially, I think being a mentor for the AI project will put you on like a pathway to becoming an event lead. And so, yeah, we're still recruiting. We're still a growing team. We still need a lot of people. So I think being a event lead would be a great way, or being a mentor would be a great way for doing that. Yeah.
If you want to apply to be an event lead, we have our form here. We look on this kind of on a rolling basis, so please apply. Yeah, so Asian projects are every quarter. We run it every quarter.
Wait, Catherine's here.
Oh. Hello.
I was here the whole time.
Really? I didn't notice you. Oh, this is Catherine. Catherine is used to be the director of operations for ACM AI. Pretty cool person. Read that snap this summer.
True.
Great workshop, guys.
Yay.
Fog.
True.
Wait, Stone.
What?
So are you available on Sunday to discuss applications for projects,
Yeah.
or do you want me to just take over for that part?
I kind of want to be involved in at least person selection.
Okay, so it's at 10 p.m. on
10 p.m.
Sunday.
Okay, I'll try to make
Yeah.
it. Oh, let me stop
Um,
the recording. I was
So
recording.
just reviewing the slides in general.